This problem is yet another problem in the set that deals with the complete analysis of a heat engine, refrigerator, or heat pump. In this case, what we're analyzing is an engine. This particular engine is especially instructive because it contains a mixture of both isothermal processes and adiabatic processes. These are the two that students most often tend to confuse with one another. The adiabatic process is the one in which heat does not flow, and the isothermal process is the one in which temperature does not change. However, these are not the same process. When heat does not flow, the temperature does change because internal energy is converted directly to work. When the temperature does not change, the heat certainly does flow because in this case, the heat is converted to work. Let's look through the problem and select the information that we're given. 2 moles of helium gas are used in this engine, and we recognize that helium is a monatomic gas. The importance of whether the gas is monatomic, diatomic, or polyatomic is in selecting the values of the specific heats C sub V and C sub P. We get these from a table that we remember from earlier in class. This table shows us that in the case of a monatomic gas, the C sub V is going to be 3/2 R, and the C sub P is going to be 5/2 R. Those are the values that we'll keep in reserve for use when we calculate the process table. These 2 moles of monatomic helium gas are taken through the cycle shown in the figure below, A to B to C, and then returning back to A. The device is used as an engine. We recognize that because the device goes in the clockwise direction, expanding when the pressure is the highest and contracting when the pressure is the lowest. Therefore, it is certainly an engine. We're told that at point A, the temperature is 500 Kelvin, and that the pressure at point A is 400,000 pascals. Finally, we're told that during the process of A goes to B, the volume of the system quadruples, which means 4 times. In part A of this problem, we are to fill in the so-called state table, and we will mostly rely on the so-called equation of state, PV equals nRT, which is that equation that relates the 3 state variables, pressure, volume, and temperature. At point A, we're already given 2 of these values, stating that the temperature is 500 Kelvin and that the pressure is 400,000 pascals. Since we have 2 out of the 3 quantities in the first row for point A, we'll be able to solve the ideal gas law for the volume, giving us V equals nRT over P, and we can simply plug in our values in order to get the volume at point A. The result is 0.0207875. As always in these problems, we're keeping lots of digits since we recognize that at the end of the day, accurate answers will require that we keep many digits throughout the problem. The text of the problem specified that the volume would quadruple in getting from point A to point B. Therefore, we quadruple the result that we have to find that the volume at point B is 0.08315. In general, to solve the state table, we're going to have to use the properties of the curves that make up our PV diagram at least one time each. In this case, in attempting to find information about point B, we recognize that we know everything about point A and that A and B are connected together by an isothermal curve. Isothermal means the temperature is the same at all points, and therefore we use that to decide that the temperature at point B is 500 Kelvin. Now that point B has 2 out of the 3 quantities filled in, we again turn to the ideal gas law to fill in the third quantity. Since the pressure will be nRT over the volume, we're able to plug in all of these numbers and get the result 100,000 pascals. In attempting to calculate quantities at point C, we recognize that C is connected to B via an isochoric or constant volume curve, and C is connected to A via an adiabatic. We're going to have to consult the properties of both of these curves in order to learn what's going on at point C. Let's begin with the simpler one, which is the constant volume curve. Since B is connected to C by a constant volume process, C and B must have the same volume, and so we can simply copy the value 0.08315 as the volume at point C. We're almost done, however, we are left with two unknowns. The information that we have not used is we have not used the fact that A and C must be connected by an adiabatic curve. The adiabatic curve by some is considered to be slightly more complicated than the others because none of our three quantities, pressure, volume, or temperature, are held constant. As a result, the relationship among points along this curve is somewhat more complicated, and substituting C for point 1 and A for point 2, these relationships are as follows. Pressure C, volume C to the gamma, equals pressure A, volume A to the gamma, and temperature C, volume C to the gamma minus 1, equals temperature A, volume A to the gamma minus 1. We know all values at point A, the right-hand side of each equal sign, and we know the volume at point C. Therefore, the first equation has as its only unknown the pressure at C, and the second equation has as its only unknown the temperature at C. Let's solve for the pressure at C. The pressure at C will be equal to the pressure at A times the ratio volume A over volume C to the power gamma. Because the helium in this engine is a monatomic gas, the gamma will be equal to 5/3, telling us that the pressure at C will be equal to 400,000 times 1/4 to the power of 5/3, yielding a pressure result of 39,685 pascals. Finally, we can calculate the temperature at point C either by solving the ideal gas law for T or by using the TV relationship for an adiabatic curve. Either result gives us the same answer, which is 198 Kelvin. Now that we have completed the state table, so we know the pressure, volume, and temperature at all three endpoints in our diagram, we're ready to proceed to the process table. Good news in the process table. 3 of our 4 processes have a 0, either as W, Q, or delta U. The only process that has no zeros is the constant pressure process, and in this diagram we don't have that one. This means that while calculating each of our 3 processes, we will only have to do a single calculation and then refer to the first law of thermodynamics, delta U equals Q minus W, to get the missing value, which will either be the one we previously calculated or the negative thereof. So let's begin. Process A goes to B, as we'll remember, was isothermal. Listen carefully. Temperature is related to internal energy. Isothermal has constant temperature, therefore it has constant internal energy, therefore the delta U for an isothermal is 0. Meaning that all we have to calculate is either W or Q in order to be finished with the problem entirely. We're going to calculate W, which looking up in the table is going to be nRT times the natural log of V2 over V1. In the case of A goes to B, it is the volume at B, which is the second one, so that's V2, divided by the volume at A. Plugging in the values for all of these at points A and B, we get the result 11,527 joules. When delta U is 0, Q equals W, and so we get exactly the same value for the heat. The next process is B goes to C. B goes to C is a constant volume process. Work is the integral of pressure over change in volume, dV. If we don't change the volume, we don't do work, and as a result, B goes to C has no work associated with it. In the case where there's no work, delta U is equal to Q, and we need to calculate either one of them to learn them both. Fortunately, the formula for delta U is always the same. It is N C sub V delta T. Notice, please, that in getting from B to C, the final point is C. Thus, in the process B goes to C, the temperature has dropped, and therefore the change in internal energy is a negative number. Furthermore, since C sub V for a monatomic ideal gas is 3/2 the ideal gas constant, we are able to plug in 2 moles, 3/2 the ideal gas constant, times the quantity 198 Kelvin minus 500 Kelvin to get a change in internal energy of negative 7533 joules. Now that we have 2 out of 3 quantities in the process B goes to C, we're able to get the third by referencing the first law of thermodynamics, which says that when W is 0, delta U is equal to Q, so that we have a negative 7533 joules also for the heat. Our last process in this diagram is C goes to A, which is adiabatic. Adiabatic is one of those processes in which we have a 0. There is no heat flow during an adiabatic process, meaning that delta U is minus W. Well, the delta U calculation is going to be an NCV delta T, just like it was in the previous line, just like it is in any line. The only difference is, rather than going from 500 down to 198, we're going up from 198 to 500, and so we get the result positive 7533 joules as the delta U. Referencing again the first law of thermodynamics, when Q is 0, delta U is minus W, so the work involved in this process is negative 7533 joules. All of this makes sense. Look at the work column. From A goes to B, the volume increases and the work is positive. From B goes to C, the volume remains the same and the work is 0. And finally, from C goes to A, the volume decreases back, therefore the work is negative. But since it was always at a lower pressure, there is less negative work than positive work. We can now calculate the totals all the way across. We have positive 3944 joules of work overall, 3944 joules of heat, and no change in internal energy. This line makes sense, and so we're ready to move on. Why does it make sense? Number one, since a complete cycle returns to the initial temperature, the total delta U must be 0, and it is. This means that Q should equal W, and they do. Finally, since our diagram goes in the clockwise direction, this is an engine, and it produces work rather than requiring it. Therefore, W and Q are both positive. This calculation is correct, and we can move on to part C. The solution to part C is explicitly dependent upon what kind of device that we've made. And so let's do a reminder of what these devices do. An engine draws in heat from a hot place, making Q hot positive, and expels heat to a cold place, so Q cold is negative, and in the process gives us work. A refrigerator or heat pump, on the other hand, are driven in the reverse direction by applying work. When you apply the work, you take heat away from the cold place, meaning the heat goes into the engine from the cold place, making Q cold positive, and you dump heat into the hot place, making Q hot negative. As we examine our calculation, we'll see that there are 3 steps during which we calculated heat: A to B, B to C, and C to A. Each one of these either makes a contribution to Q hot or Q cold, and we determine which one by looking at the signs. Q hot will be the sum of all positive contributions. There's only one, so Q hot is 11,527 joules. Q cold is the sum of all the negative contributions. Therefore, Q cold is negative 7,533 joules, and we have identified both Q hot and Q cold. Finally, to complete the problem overall, we must collect 3 summary pieces of information. First is the total work of 3994 joules. Second is the heat that came in from the hot place, Q hot, which is 11,527 joules. And finally is Q cold. This is the heat that was expelled to a cold place. Because it was expelled, it is negative 7,533 joules. These 3 numbers will be analyzed to tell us how well our engine is performing. Once again, just as in part C, how we perform this calculation depends upon what kind of a device that we have. However, they have one thing in common. Each one of these devices provides you with something. This is what you get from that device. Each one of these devices takes something from you. This is what you paid for. We always determine the quality of any transaction by dividing what we get by what we paid for. In the case of an engine, we get work. We got our work by drawing heat from the hot reservoir. Unfortunately, we expelled some to the cold, and so we have a finite efficiency, work over Q hot. If we had instead done a refrigerator, we built a refrigerator in order to cool our food. Therefore, Q cold is what we got, and we paid for it with work in the form of electricity coming out of the wall. So the performance coefficient for a refrigerator would be Q cold divided by the work. Finally, we ran a heat pump in order to heat the living room, so we deposited heat into the hot place. Q hot is what we got. We paid for it by using electricity from the wall in the form of work, and so the coefficient of performance is what we got, Q hot, divided by what we paid for, which is the work. Finally, it's worth noting in each one of these lines the range of appropriate values for these quantities. An engine will go from 0 to 1 because you can't have more than 100% efficiency. However, for the case of both the refrigerator and the heat pump, the ideal device uses no work. And so the 2 quantities, Q cold over work and Q hot over work, are not efficiencies. They are coefficients. And their values actually range from 1 to infinity. Because we have an engine, we will be taking work over Q hot, and our expectation is that we will get a number that is less than 1. As specified in the table, the efficiency is the work over Q hot, and we've collected our total amount of work in one cycle of 3994 joules, and we paid for this with an influx of 11,527 joules, meaning that our engine has an efficiency of 0.346 or 34.6%.